Hello! In this video, we will talk about how REVEN can help with analyzing a malware. More specifically, we'll analyze a light recent version of the Uroburos malware. We recorded a trace that's about 50 seconds long, where we started the malware's dropper, and from that trace we'll see, first, that by connecting third-party tools, we can detect compromission of the system and use the hooks in place as entry points for our analysis. Second, that by using the taint engine, we can get a good idea of the dropping mechanisms the malware used. And finally, that by using the Python API in conjunction with manual analysis, we can dump all binaries involved, including those that don't appear on disk or somehow try to hide. This is what the trace looks like. It's pretty simple. We start the dropper binary, and then it looks like nothing happens. And about 50 seconds later, we stop the recording. So the first step here is to check for compromission. Thankfully, REVEN integrates well with the tool Volatility, and although usually using it would require having a core dump of the virtual machine, here it can simply be connected to any moment of the recorded trace. It's about 3.5 billion instructions long, so if we assume that the malware is fully loaded near the end of the record, we can use the command callbacks at about 3.5 billion instructions and see what happens. So pretty quickly we get the first results, and this one is particularly interesting. There's a generic callback set by an unknown module. Let's stop the command here. So let's look at that address to see if it's executed somewhere in the trace. Yes, it is, multiple times. It belongs to an unknown binary. This might happen when we cannot find a binary on the disk. It's called on process termination, which means it's probably been set up through a call to create process notify routine. So let's look for that. There's one match. Let's look at the first argument to that call, and this is the address of our unknown callback. If we get further inside create process notify routine by skipping a few things, we see the table where the callback structure is stored. And the algorithm here is going to look for the first empty entry in this table to store our callback. Right there. That means we could use the memory history on that table to detect row callbacks that are not set up using the create process notify routine. We could also monitor other types of callbacks, like create thread notify routine. In this case, there aren't any. Or we could look for network callbacks. There are some, and again, they are called by our unknown binary. So we know the malware is also setting up hooks on network activity. Note here we could have also analyzed the array of callbacks just like we did earlier. About this unknown binary, perhaps it's time we try to see where it's coming from. So let's have a look at the dropping mechanism. I'll take any executed byte of the unknown binary and taint it backward. For my current moment in time, up to the start of the trace, taint 1 byte. In a couple of seconds, what I get here is a list of copies. Note that the results go back more than 1 billion instructions before the taint starting point. Actually, what we see here is the entire dropping process, including what's happening inside the kernel. Now all I have to do is look at each successive copy to understand what happened. The first one takes me to a memcopy call. Looking at the destination buffer, we can verify that we are indeed writing a PE image. So let's place a bookmark here. The second item in the list doesn't tell me much. But the third one shows we're using a driver called USB eHub. Now that's interesting because there exists a legit Windows driver called usbhub.sys, and this name USB eHub is obviously an attempt at hiding in plain sight. Again, let's place a bookmark. The next operation in the list is a memcopy, instructed by an anti-device IO control file. And if we look at who called it, we find a binary called pxinc64. This binary seems to be the junction between user mode and kernel mode for this malware. So again, let's place a bookmark. Continuing the analysis, we find our binary until we finally reach the initial dropper binary. Now that we've seen all stages of the dropper, let's see how we can actually extract the binaries involved so we can load them in IDA, analyze them, etc. Going back to the first memcopy, we can see what is going to be the base address of our binary. But note that this binary does not appear on disk, so there's no file we can dump, and dumping the loaded image right here is not going to result in a clean binary. So instead, we'll use Volatility's ModDump module to reconstruct a PE file from the loaded image. Let's assume the binary is still loaded toward the end of the trace, and launch the appropriate command to the base address. Well, it didn't work. What's going on? If we look at the base address toward the end of the trace, indeed, the magic has disappeared. Using the memory history on that, and looking at the content before the last write, it's easy to see that this magic has been overwritten. So let's try to dump it again, but this time before the magic has been overwritten. And this time it works. I can now load that PE file into my favorite disassembler. The next stage in the whole chain was the USB eHub driver, so let's see where it's coming from and how to dump it. To do so, I'll use the same methodology we used on the unknown driver and taint any executed byte. From my current transition, again backwards to the start of the trace. There are only a few entries, so I can take them in chronological order this time. The first one is just the disk loading the file. Then the initial dropper copy, followed by an anti-write file. Next, the driver is loaded, and with C this involves a cryptographic validation with CI validate image header here. Finally, the binary is copied so it can be loaded. In this chain, the best moment to dump the file is during the anti-write call, since this will get us a valid PE file directly, including any signature the driver may have. So let's dump the memory buffer that got written. Going back to the anti-write file call, right here, and if I skip the syscall and the Windows on Windows 64 back to the userland write file call here, the buffer is mentioned there, and this is its size. Using this information, I can run a script to dump the memory. This is the location and this is the size. Now let's have a look at this file. First, it's interesting to note that dumping the file as is preserved the driver's signature. Then I can load this file in IDA, which tells me it's the infamous VBox driver. Finally, using the open source plugin RedSync, I can sync IDA's views on REVEN, loading our connector plugin, the two views are now in sync and I can get more context, explore unexecuted paths, etc. Now, we'd like to dump the last binary called pxinc64. Again, I will tend a byte and try to look for a call to anti-write file. There's one here. Going back to the userland call, again skipping the Windows on Windows 64. This is the address, and this is the size. Let's dump it. What happens if I now load this file in IDA? Well, it appears the binaries don't match. What's happening then? Well, the taint suggests there's a lot of activity that we skipped here, so maybe we should start from the end instead of starting from the beginning. What is copied here? Going back to the origin of that copy, in userland, I see that the code is actually copying over itself. If I search for matches to that call, there are some. By iterating over these, I can see that the code seems to be overwriting multiple sections of itself. And although it writes over the loaded image, if we look at the source, back when we wrote the first section, it seems that it's stored as a regular PE file. perhaps in the binaries resource. So let's try to dump this source instead. Here is the origin. And here is the last written section, which I can use to compute the size of the dump. Now let's load that in IDA and see if the synchronization works. And indeed, the binaries now seem to be similar. To sum up, we've been able to find the code responsible for the system's compromission, even though this code was running in kernel mode. We've also analyzed the process dropping a malicious driver and dumped the various stages as valid PE files, even though they did not touch the disk or were altered in the process, to allow analyzing with regular static tools. If you found this content as interesting as we do and want to know more about it, or REVEN in general, do not hesitate to follow our blog for more content, or contact us via the website or contact@tetrane.com.